Good morning, everyone. I hope you're all having a great time at RSA. And yeah, let me start by introducing myself. I'm Divyansh, and I'm a data scientist in the applied data science group at Nvidia. What I do is I work with some diverse internal teams like marketing, cyber ops, supply chain, and build custom AI solutions. So a couple of years ago, I got this great opportunity to work with some really talented cybersecurity researchers at Nvidia. And we discussed how asset management was a big pain point for them. Understanding what's on a network is critical in how we secure our digital assets. So together, we came up with this new and exciting approach to map network devices using graph-based artificial intelligence technique. AI in cybersecurity has evolved from a nascent technology to a critical tool that organizations use today to fight cyber threats. It has become even increasingly more important with the growth of digital data and the complexity of the cyber attacks that we see today. It has the potential to significantly enhance the cybersecurity capabilities by providing advanced analytics, automation, and decision-making capabilities that are critical to cyber threat detection, prevention, and even response. So let's get started. This is the disclaimer I have to show you for 5 seconds for legal reasons I don't understand. Okay, so this is my first time at RSA, and I'm honored to have this opportunity to be here and speak with you all. Some of my colleagues at NVIDIA have presented at RSA before. In fact, this is their presentation from last year, where they shared some interesting approach of using GPU-accelerated machine learning techniques to detect anomalous user and application behavior. It's very interesting, and I highly encourage you all to check it out by scanning this QR. So this is what we plan on talking about today. First, we'll start by defining what is asset management and why you should care about it. Then we'll talk about some of the current approaches and challenges associated with this domain. Next up, we'll talk about graph autoencoders and clustering, which are the AI techniques we use for this solution. And finally, we'll see how you can get started with this approach to map assets in your own organization and detect cyber threats. So any corporate network has thousands of devices on it at any given point of time. Asset management is the process of identifying, tracking, and managing those assets. A strong asset management policy can bolster the cybersecurity defenses of any organization and help it to identify potential vulnerabilities. On this slide here, I have some statistics on how a weak and inefficient asset management can cause serious reputational and financial damage to an organization. So how do we do asset management today? There are two broad approaches, active asset management and passive asset management. In active asset management, we collect information by polling the assets on the network. These assets could be switches or routers, and the information can be collected via SNMP, CLIs, or APIs. We can also scan the network using live agents and detect every login attempt or connection. In passive asset management, we're only interested in listening on the normal broadcast traffic. That is, we are not generating any new traffic in the process. Some examples of passive data sets could be NetFlow events, syslogs, event-based logs like Windows event logs, etc. Both of these approaches have their own benefits and drawbacks. Active asset management can give us a more accurate picture of what's on our network, but it can compromise the network bandwidth. What's good for your network depend on the number of assets in your network, the complexity and the structure, and other factors. In our exercise, we predominantly use passive data sources as they were easier to collect without flooding our network with live agents. The biggest challenge with asset management today is the scale. There are so many devices that are spread across different locations and platforms, and this number is constantly changing. New devices are being added and removed from the network at any given point of time. Moreover, the tools that we have at our disposal today often work in silos, and there is no good way to integrate all of that information. And this is where we feel AI can help. AI can automate the asset discovery process by analyzing these network logs and data for us. It can go a step further and divide these assets into meaningful groups based on asset behavior, and then we can customize our policies for each of those groups. Finally, it gives us a way to leverage all these data sources and their various strengths to come up with an effective asset management policy. So let me introduce our solution. We use something pretty cool called graph neural networks. Graph neural networks, or GNNs, are neural networks that work when the input data is in the format of a graph or network. So you may ask, why do we want to use these GNNs for asset management, right? It's a fair question. Well, because our corporate networks can be very well represented as graphs, and these GNNs are very well equipped to ingest or process large volumes of heterogeneous data. When we combine these benefits of GNNs together with the powerful parallel compute of GPUs, we have a strong base to solve this problem. Let's talk about graphs for a moment. What are graphs? Graphs are any combinations of nodes and edges. A graph can be anything. For instance, social connections where people are connected to one another, or molecules where atoms are connected to one another. So we'll try to understand some basic graph terms with the help of this social connection example, for instance. People can be represented as nodes. The relationships or friendship between people can be represented as edges. And each person will have specific characteristics like age, where they live, their job titles, and all those characteristics that are specific to a node can be represented using node features. This is all the information that we need to know about a graph to get started with GNNs. So I'll talk about the use cases that this approach can serve. Starting with our passive data sources that I mentioned a while back, we have NetFlow, event logs, and SFlow that we use. But you don't have to limit yourselves to just these data sources. You can use any data source that's available to you. The idea here is to come up with a graph representation of a corporate network. Each node in this graph is an asset in our network, and the connections between, or the edges between those nodes can be derived using this data source. Once we have the graph representation ready, we can use it as an input to the graph neural network model. The graph neural network model takes this graph and tries to come up with an accurate representation of each of each node in this input graph that is an asset. And this is done via asset embeddings. Embeddings are a way to represent data, in this case asset properties, in lower dimension as a set of numerical values. These values capture the essence of an asset and can then be used for different use cases downstream. So for instance, we can use these embeddings to predict the type of asset. For instance, if this embeddings are part of a SQL server or they belong to a workstation or a laptop, we can also see how different embeddings from assets work together to form a service, and that will come under service discovery. If we use these embeddings together with the network topology, we can try to understand the impact radius of any incident and then aid in its quicker resolution. And finally, if we use these embeddings as input to the clustering module that divides our assets into different groups, we can identify vulnerable devices and detect suspicious activity. I'll talk about this particular use case later in the presentation. So the kind of graph neural network we use is called a graph autoencoder. It has two components, the encoder module and the decoder module. Like we mentioned before, we represent a corporate graph as in a graph representation, and this graph representation is input to the encoder module. The encoder module takes this graph and comes up with asset embeddings. These asset embeddings are then used as input to the decoder module. The job of the decoder module is to take these embeddings and try to reconstruct the original input graph. In other words, the output of the decoder will look very similar to the input of the encoder. Why do we do this? Why do we take this graph, learn embeddings, and then transform it back to the input graph? Well, practice. We want the model to learn. We want the model to learn and minimize this reconstruction error from the output of the decoder and the input to the encoder. Once the model has learned with practice, it is able to accurately represent each of this asset via embeddings. And once we have those embeddings, like we talked earlier, we can use it as input to the clustering module and use any clustering algorithm to divide our assets. Now, I mentioned that we can use these graph representations as input to the GNN, but how exactly do we do that? There are two sets of input features that we need to talk about: the adjacency matrix and the feature matrix. Both of them provide important context on the assets and its neighbor to the network. The adjacency matrix tells the model about which assets neighbors an asset interacts with, whereas the feature matrix informs the model about specific properties of an asset. We'll try to understand this better with the help of an example here. So we have a small network with 4 assets: a web server, a laptop, a workstation, and a SQL server. All these 4 assets interact with each other using different ports and protocols. And now we'll try and come up with their adjacency matrix and feature matrix. Since we have 4 here, the adjacency matrix will be a 4x4 matrix, where each element of the adjacency matrix represents a connection between 2 assets. So for instance, if you look at the first row here corresponding to this laptop, we'll see that because it talks to this web server and the workstation, we'll have we'll have that entry in those corresponding cells. Similarly, if you look at this SQL server, because it only talks to the workstation, there is only going to be a 1 in this corresponding cell. Now coming to the feature matrix, we'll try and use this laptop as an example. We see that this laptop talks to 2 other assets, so we'll have a node degree of 2 here. But if we were looking at, let's say, any other asset like a web server, this would have been 1. We can also derive other features corresponding to the ports that are used by this asset, the total number of net flow events, the average packet size, the protocols that are being used, and whether it engages in unicast, multicast, or broadcast communication. These are just some basic examples that I've used for this illustration. You can obviously get even more creative and use more examples depending on the data sets you use. In our exercise, we use close to 70 features for each asset. Let me talk about the second component of our AI-based solution, clustering of the assets. Clustering is an unsupervised machine learning technique that helps us to identify groups or cluster within the data set. What's special about clustering is we do not have to give it any prior information on the labels or the groups. It is able to decipher that information on its own by looking at the underlying structures and patterns within the data. So with clustering, our basic hypothesis or premise is this: assets belonging to the same cluster will behave similarly, and assets across different clusters will behave differently. And once we're able to divide these assets into different groups, we only have to monitor communication between different asset groups to detect suspicious or anomalous behavior. There are 2 major clustering approaches: hard clustering and soft clustering. In hard clustering, we assign each data point or an asset a definitive group. In soft clustering, it allows for mixed memberships of an asset. That is, an asset can belong to 1 or more group. So k-means is an example of hard clustering technique. The k in k-means stands for the number of groups or clusters that we want to identify. And this is an information or parameter that we have to specify in the beginning. The way k-means works is it takes each asset, assigns it to the nearest cluster centroid, then calculates the mean of all the data points in each cluster and updates the cluster centroid. And this process keeps on repeating until the clusteroid does not change or a fixed number of iterations have passed. So this image that you see here is the result of applying k-means on the asset embeddings of our own corporate network. And what we observed was something very interesting. 91% of the communication that happened was between assets belonging to the same group. So if I am an analyst and my goal is to, let's say, understand or detect suspicious behavior, asset behavior, I can start by only looking at 9% of this communication. And I don't have to spend all of that time and look at all the communications out there. I think that's pretty neat, and I have highlighted 2 examples in this case study that are interesting for us to look at. Right, so if you look at the image on the left, we have a network equipment that's part of the green group, and all the other devices that it talks to belong to the same green group, except one device that's part of the pink group. Now, when we looked at this data even more closely, our eyes lit up. What's happening here is when the network equipment is talking to all the other green devices, it's using a standard TCP protocol. But when it's talking to the pink device, it's using an unsecured NTP protocol. Now, if you're not aware of NTP, it's Network Time Protocol, and it is used to synchronize time between multiple assets on the network. Some older versions of NTP are unsecure, and let's say if this network synchronization or time synchronization packet is intercepted by a malicious actor, it can compromise our network and even result in DDoS attacks. This was a big red flag and vulnerability in our network. And yeah, so this example was able to kind of highlight that. If you look at the image on the right, we had 4 assets, 3 of them belonging to the pink group and 1 belonging to the green group. Again, when we look closely here, when the pink devices were communicating within themselves, the average packet count was low. But when this pink device was talking to the green device, the packet count shot up. This was highly unusual, and what we eventually concluded was that these 2 devices should not even be talking to each other in the first place. This green device had no business being here. As we can see, the model is able to pick up on subtle trends and patterns like this and assign these assets to the right group. Finding vulnerabilities in our network or understanding the root cause of network incidents is like finding a needle in the haystack. What the model does for us is it tells us where to look. Now, I mentioned soft clustering a couple of slides ago, and HDB scan is a density-based soft clustering technique. It is able to identify clusters of various densities and shape without any prior knowledge on the number of clusters. This is a key advantage over a hard clustering technique like k-means. The way it accomplishes this is by grouping together data points or assets in high density region together while ignoring the data points in low density region. In other words, what the model believes is that these assets that belong to the low density region are so different from any other assets or asset groups on the network that they cannot be assigned a cluster. This subset of devices with unassigned clusters can be vulnerable as they do not behave like any other asset on the network. Now, switching gears for a moment, we've seen how we can use these AI techniques to analyze complex cyber logs like NetFlow data, sysflow data, syslogs, and Windows events, and divide our assets into different groups and observe anomalous asset behavior. The volume and the velocity of the data that is needed to make something like this happen requires a solution with low latency and high throughput, which is why we use Nvidia Morpheus for deployment. Morpheus is an open source SDK for cybersecurity use cases. It is data agnostic and can ingest data from all of the aforementioned data sources. It is user-friendly, and users can customize their pipeline or workflow based on their particular cyber use case. It combines the best of NVIDIA technologies like CUDA, Rapids, which is our compute engine, TensorRT, and Triton Inference Server. It is 100% GPU accelerated and can be configured in different settings like on-prem, cloud, or hybrid. Now, this is what this model pipeline would look like in deployment or production. And it's important to think of this pipeline as discrete independent stages. So we have a pre-processing stage, a training stage, and an inference stage. We use the data sources that we have talked about so far to come up with a graph representation in the pre-processing stage. In order to come up with that graph representation, we'll need to extract the nodes and edges for that graph. Once the graph representation is ready, We can then use it in the training stage to train our graph autoencoder, learn the asset embeddings, and then use the clustering module to divide our assets. Then we have a stage where we do not have to train the model again. We can use these pre-trained or pre-learned embeddings to make predictions on real-time data to detect anomalies. Like I mentioned before in the last slide, Morpheus does the heavy lifting for us here by taking care of deployment, orchestration, and back pressure automatically. With all of that background information, I hope you're excited to see this demo in action and see how useful this is. So what we have here is about 10,000 assets from a corporate network. And what we're going to try and do here is filter this based on specific node criteria. I apologize if this visual is not super clear. So we're going to select network. We're going to select the node type or the device type to filter this view. So we're going to select network devices and see how all the different switches and routers are spread across different clusters. Now we can also go back and filter this based on the ML groups that we have derived from the clustering module. So let's say I want to look at all the assets belonging to a specific group 1. So I can go ahead and select that from the drop-down menu and see. If I want to look at how assets from multiple groups interact with each other, I can select multiple groups here and then zoom and see how those specific assets interact. Here I have some very basic filter criteria for this visualization, and you can obviously add more filters based on what's important to you. For instance, if you only want to look at assets that have been active in the last 24 hours, or you want to look at assets that talk to other assets across different groups, you can also do that. Well, this was how we tried to do asset clustering on our network. And if you thought this was cool, and if you'd like to try it out as well, I recommend that you start by downloading the open source Morpheus SDK and start by exploring the data sets you have in your own network. You can play around with some pre-built models and pipelines that are available in Morpheus. And once you're slightly more comfortable with the pipeline, the data, and the model, you can customize your own workflow to come up with the asset maps in your own organization. And yeah, so please give this a go, test it out, and I'm excited to see what you come up with. This concludes the presentation, and I hope this was helpful for you. If you have any questions, please feel free to come up to the microphone, or you can chat with me after.
Thank you for presentation. I have a couple questions. First of all, I would like to ask about hardware locket. If I want to use Morpheus, I want to have only Nvidia hardware or not?
No, so Morpheus is open source. You can download it, you can use the model that's available there, you can use the pre-processing tools. The benefit you get from having Nvidia is it's GPU accelerated. So these DNNs are generally compute intensive. So if you have GPUs to kind of support that, but that's not like the only requirement. You can still execute and use the code and the models that are available there.
But if you speak about data source, I mean, if you use hardware from Nvidia, we automatically will get a right data source for Morpheus, yeah, without any efforts, for example.
So are you asking if you have to stick to certain data sources if you use Morpheus? No, so like I mentioned, we used a bunch of these data sources like network flow logs, S-flow logs. This is not specific to any company or any organization. Every organization has it. And there are parsers available for you to parse this data so that your data is ML ready.
Okay, and my last question, I would like to ask about, imagine the situation, we have thousands of assets, and after that we want to add a new one, yeah? My question is, what exactly bunch of data from new asset we need to have for asset discovery, management, detection, something like this? What this particular time, or how many flow we will have, and something like this?
Yeah, that's an interesting question. So when you have a new asset that pops up on the network, what we can do is and this exercise of running or creating your asset maps and asset groups can be done periodically, right?
Yeah.
Say you run it at one time and this asset is not there. Next time you run it, it pops up in a cluster. You can see, because of the embeddings, which other assets it's closest to. And over a period of time, you can monitor if it's shifting groups. So let's say you had the asset in one group, and 2 weeks later, if you run this and it's part of other group, whereas the other assets have kind of stayed the same, then you'll be able to understand a trend and see why it's kind of moving across different groups.
Other words, all time our embedding will change because some assets will active or not, yeah?
Sorry, I didn't understand.
I would like to say the embedding which describe our asset will change all time, because some asset will be active, some asset won't be active, and after that we need to recalculate embedding very often, because our network, for example, change or not.
Yeah.
So how you update the graph features? We update the graph features every time when we need to get some information from asset discovery, or for example, it happens real time.
Yeah, so like I said, the frequency of when you kind of update your embeddings will depend on how often do you want to run it. So for our case, we found that running it in 2 weeks was optimal, because when we ran it like on a sequential every day or every week, we thought the embeddings or the groups for those assets weren't changing that drastically. 2 weeks for us was the right time, but again, you'll have to see for your own organization what's the right frequency.
Okay, I see. Thank you very much.
Yeah. Sure, yeah. I'll make sure I talk to RSA and make this available on the portal. Yeah, thank you.
Hi, Divyansh.
Hi.
Thank you for the presentation, making it in human language. Even I understood it. What you're trying to get at. I have a couple of questions. The first one was on slide 12, and I think you answered it partially later on about the pre-processing, converting your, your raw log data into graphs. That's the hard part, and that depends on, the preprocessors, right? So there must be a finite set of preprocessors that the SDK supports.
Yeah, so it has built-in parser, for example, Windows event log.
Okay.
So you have your Windows event log like 4624. That's particular to a login activity.
Yeah.
So it's able to parse all of that information, and because we have a source and destination, we're able to construct that asset map.
Okay, great. The other thing is, in the example you gave was a fairly simple example as a 4x4 matrix. However, in reality, you have tens of thousands of assets, and you don't have a single edge, right? There are multiple edges, right? So it becomes complicated. It becomes a multi-dimension. I'm sure it takes care of it. However, what does happen with this is, while visually appealing, the visual is not actionable, right?
True.
So is there a way to also convert things like anomalous assets into a narrative kind of a thing? And it's a two-in-one question. A lot of times, it's not a new asset that is exhibiting malicious behavior, but it's a existing asset that's been compromised and will exhibit malicious behavior for a small fraction of time and then go back to normal, right? So that is the kind of anomaly that you want to highlight.
Right.
Is there, does Morpheus support some, being able to pull out, time-sliced anomalies?
Yeah, I'll try and answer your questions.
Sorry about so many questions.
So what happens here is, I talked about some of the use cases, right, in the slide, where we can try to detect the root cause of any incident based on the impact radius. So let's say one of the assets in our network goes down. So and it talks to, let's say, 100 other assets. So rather than troubleshooting all those 100 assets and looking at, okay, which other assets could be affected first, I can start by looking at the embeddings and see which 2 assets or which 3 or 5 assets are closest to that, and then just start by looking at that radius. So that kind of gives me an actionable insight into, okay, how, if an incident happens, I don't have to look at all the other devices that this particular asset could be talking to. And similarly with the anomalous behavior example you mentioned, we'll see that, let's say, this asset interacts with a certain assets in the same group. When you run this embeddings exercise again after a few weeks or a few days, you will see that it's starting to access assets across different clusters now, because it's trying to, let's say you have a server in your supply chain and it's trying to access marketing data and things like that.
Yeah.
So that will show up here.
Okay. So, I mean, the question is, say, where some nodes features have changed in a certain time slice, or some way to highlight that.
Yeah.
That kind of.
So in terms of highlighting that, you can have, like I showed some basic visualization, but you can have a dashboard that's customized based to what's important to you, right? One example is assets that have suddenly started talking to 3 or more other assets from different clusters.
Yeah.
So that could be an example. And in terms of visualization, there are, I know cuGraph is a tool that is part of Nvidia's ecosystem that gives us a fast way to visualize all of these assets without the lag.
Okay. Thank you very much. Very well. It's really good work, useful work.
Thank you.
Hey, question for you. So what is the encoder actually learning?
Right. So what the encoder is learning is, you have the input features, right, and the adjacency matrix. Those 2 sets of input features. Let's say you have 70 input features and you have 10,000 matrix. It's able to capture the essence of those assets, of these features, into a lower dimension. Let's say only a 10 by 10 in a 10 vector representation. So you're able to encode all of that information as a set of numerical values, a short set of numerical values that you can use for any use case.
Now, is it looking for like similarity between nodes or something? Like what's
Exactly. So let's say I have an asset that's represented with 10 values and I have another asset that's represented with 10 values. If I use cosine similarity or any similarity kind of tool, I would be able to see how these assets are closer to each other or different from each other.
And that's what the embedding is learning.
That's what the embedding does.
So can you not just use that, and why do you need the decoder as well? Like you could just use that output of the encoder itself.
Yeah, so I'll try and explain it in this way. Because we need to tell our encoder what to optimize. Every neural network needs a loss function that it needs to optimize. So we want the network to learn how to accurately represent that. The decoder is taking that embedding and tries to reconstruct the original graph.
Yeah.
So when we have a feedback loop or a reconstruction loss from the decoder to the encoder, so it's telling it that, okay, the graph that you recreated is probably not right. You need to optimize it a little more. And then it will keep on changing this embedding until the input of the encoder and the output of the decoder look very similar, or the reconstruction loss is optimized.
So I'm assuming you're taking the last layer output from the decoder as your embeddings?
From the encoder.
No. What do you actually eventually use as your embedding? Is it the output from the decoder?
No, no. So the output we use is the last layer of encoder because that is the
okay.
one that comes up with the.
But it's optimized using the decoder.
Yes, but
Got
we
it.
use the entire network to optimize those embeddings.
Got it. Okay. Thank
Yeah.
you.